It is a pleasure to introduce our next speaker, Cody Stockdale from Clemson University. The title of his talk is Sharp Weighted Quick Type Bounds for Operators.
Okay, yeah, thank you everybody for being here. Thank you for the invitation and the opportunity to speak in this conference. It's been many very interesting talks so far, so I've been enjoying it. Um, so my topic today is in the area of weighted norm inequalities and harmonic analysis. So in harmonic analysis, we're in the 50s, it kind of delineated and the theory of Calderon-Zygmunt singular integral operators was sort of born. And through this lens, um, we study the theory of weighted norm inequalities and in particular quantitative bounds for operators. And we're going to be considering weak type bounds. So this is very much related to a few talks earlier today, especially the first talk. Um, you'll see some commonalities. So, okay. So our motivation, we're going to begin by talking about singular integral operators. So formally, let's think about an operator T that takes in an input function f, multiplies it by a kernel function k of x and y. So the common variable is y. You integrate out the y variable, you're left with a dependence on x. So this is called a integral operator because it's defined by integration. And it's going to be called a singular integral operator because this kernel function k is going to be a singular function. It's not going to be defined when x is equal to y. So we cannot allow the two inputs x and y to be the same value. So that's where the word singular comes from. Um, on the other hand, in order for this theory to push through, we should assume some assumptions on our kernel function k. In particular, we'll assume that k has a growth condition, like a size condition. So in modulus, it's bounded above by 1 divided by the difference of its arguments to the dimension power. So it just it kind of decays at infinity and has some controlled blow up on the diagonal, but just barely fails to be integrable both at the origin and the diagonal and at infinity. And an additional kind of smoothness condition that we assume that it has is the following. So if you look at the difference of, for example, is this first term, k of xy minus k of xy prime. So you change the second component. That should be controlled above by the difference of the second component to some positive delta power divided by x minus y to the n plus delta. This basically is controlling a derivative of k. And if you imagine like taking this y minus y prime to the delta power, dividing it over from both sides to side, the left-hand side then looks basically like a difference quotient, like a derivative. And in a stronger sense, but for the purposes of this talk, it's okay to think of this as a condition that says that the derivative is bounded above by like a constant divided by x minus y to the n plus delta. So you get a little bit of extra integrability at infinity for these types of kernel functions. So these kernel functions are called Calderon-Zygmunt kernels. These encompass the operators that Calderon and Zygmunt famously studied in the 1950s. The integral operators associated are called Calderon and Zygmunt operators, so long as they're bounded on L2. So we say that a Calderon-Zygmunt operator is an operator of this type that also we assume a priori boundedness on L2. Investigating the boundedness, whether or not such an operator is bounded or is not bounded on L2 is a different story, um, which I don't want to focus on for the purposes of this talk. But we're going to assume the L2 boundedness from the beginning. So some examples of these Calderon-Zygmunt operators, traditionally from the late 1800s, even like 150 years ago, the Hilbert transform, which is basically this convolution with 1 over x. Its higher dimensional analogs, the Riesz transforms, which have, if you take the dimension equal to 1, this formula here collapses back to the Hilbert transform. But this operator, the Riesz transform, plays the role of the Hilbert transform in higher dimensions. Many other examples, for example, Calderon commutators, Alford-Sperling operators, certain pseudo-differential operators with symbols and certain Hormender type classes, and many, many others that I'm just using this half of a slide to justify that there are examples within this framework. So this framework is worth studying. But this framework of Calderon-Zygmunt operators has been studied since the 1950s, for the better part of a century, and we continue studying these operators. So what's called actually often referred to as the Calderon-Zygmunt theorem is that not only are these operators bounded on L2, which is part of their definition, they're bounded from L2 to L2 by definition. That's an a priori assumption, but that automatically extends to boundedness on LP for any p between 1 and infinity. So that's just, reminding ourselves what the LP norm is. And what we're going to be focused on in this talk is not these what are called strong type bounds, which is a bound from an LP space to an LP space, but what's called a weak type bound which is a bound from an LP space to a weak type LP infinity space. So by Chebyshev's inequality, this strong type bound implies the weak type bound, where we can instead replace the left-hand side with a smaller quantity, LP infinity. By definition, this quasi-norm is defined as a soup of overall positive parameters lambda times the measure of these level set where TF in absolute value is bigger than lambda raised to this appropriate 1 over p power. That doesn't matter quite so much, but the important thing here is that this LP infinity norm, quasi-norm, is bounded above by this LP norm by Chebyshev's inequality. So whenever you have a strong type inequality like this, automatically you have a weak type inequality like this down below. And in fact, not only like in this theorem above, where you have the strong type inequality for p, any p bigger than 1, you have weak type bounds for any p greater than or equal to 1. Importantly, you include the endpoint here. When p equals 1, the weak type bound still holds while the strong type bound fails. So that theorem is stated as follows. And what we're interested in is in extensions of this theory to weighted spaces. So instead of just talking about boundedness of operators on LP spaces or weak type LP spaces, we're going to assign a weight and change the measure of these LP and weak LP spaces. In particular, given an almost everywhere positive local integral function, so that everything here in the definitions are well defined and make sense, we define this weighted LP norm where we basically take the same thing, but we tack on this extra parameter W of X, like associate this absolutely continuous density to define this new measure with respect to the W. And likewise with the weak type space, we can do the same thing where we, instead of taking the Lebesgue measure of this level set, we alter the definition of the weak type norm by taking this W measure, where W is, I think I wrote down here, W of a set is defined to be the integral of W. So we just take the measure with respect to this absolute continuous measure with density W of this set. So we can generalize this and we can ask for which weights W do the bounds of Calderon-Zygmund operators extend to these weighted spaces? We know that it works for W by the classical Calderon-Zygmund theorem from 1950s, that this works for W equals to any constant function that just reproduces the Lebesgue measure. But what if you have a function that oscillates or maybe goes to infinity or has has a vertical asymptote, some sort of blow up? Uh, is it still possible that the associated operators extend to be bounded on LP or from LP to weak LP with respect to these new weighted measures? This question was answered most famously in the 1970s by Muckenhout and several collaborators in a series of papers, and was answered with a criterion that uses this, what's called the AP characteristic. So we said that a weight W is in Muckenhout's AP class if this AP characteristic is finite, where when P is bigger than 1, so you're talking about strong type or weak type bounds, you take the average of W. I'm using this angled brackets, got it right down here, as the average of W on a cubed Q, and then multiply that by the average of W to this power 1 minus the Holder conjugate P prime, all raised to the P minus 1 power. If that is uniformly bounded when you take a supremum over all cubes, or when P equals 1, we have to reinterpret what this second factor means because P prime would be infinity. So the suitable by continuity replacement for that would just be taking the L infinity norm of the reciprocal of the weight W. But it turns out that this characteristic being finite, this AP condition, characterizes exactly the weighted bounds of any Calderon-Zygmund operator. So if you have a Calderon-Zygmund operator, P between 1 and infinity, an AP weight, then yes, indeed, your operator will be bounded on LPW, as long as your W is an AP weight, including the P equals 1 endpoint, where the weak type bound is allowed, then you will still get the weak type bound for any P greater than or equal to 1. And in general, this condition is necessary, for example, for the Hilbert transform or any non-degenerate Calderon-Zygmund operator like was introduced in Manas of Empati's talk earlier this afternoon. Okay, so qualitatively, this question has been understood. We understand exactly which weights we have these bounds for this class of operators. Um, then came quantitative questions. So the main overarching question is, if we have an operator that we care about, like a Calder-Sigma operator, or later on in the talk, we'll talk about different classes of operators that come about in harmonic analysis. The boundedness, by definition, means that you have some inequality. There's going to be some independent constant C, so that the LPW norm of the output is controlled above by C times the LP norm of the input, um, where C is uniform over all F. Or for the weak type bound, the same thing, but you have a weak type norm on the left. And the question here is, how does this constant depend on the AP characteristic W and AP? We know that that's necessary and sufficient for this bound to hold, so that constant must depend on that. Um, the constant C must depend on the AP characteristic in some way. And the question is, asymptotically, what is the optimal dependence we can expect this constant to have in terms of the AP condition? Like exponentials are bigger than polynomials, which are bigger than the log stuff. That's the kind of question. We denote these values just normally with operator norms. Famously, this was studied in the 2000s and early 2010s, and extrapolation methods for considering the strong type bounds allowed for a reduction to the case to when p equals 2. So solving this question for any p reduced to just solving the question for p equals 2. And this question was known as the A2 conjecture, which is now the A2 theorem since Hootenan's famous Annals paper from 2012, where he proves that if you have a Calder-Sigma operator, any p bigger than 1 finite, and an AP weight W, then the operator norm of T from LPW to LPW is bounded above by this AP characteristic to this particular dependence, where you take the AP characteristic, raise it to the power of the max of 1 and P prime over P. And it turned out that this is sharp in the sense that you cannot do any better. Among all the AP weights, this optimal dependence is achieved. The lower bound, the fact that this was the best you could possibly do, was proved back in '93, and the question was sort of unlocked and made aware of by a paper of Buckley, and finally, almost 20 years later, Hooten proved the optimal upper bound for this general class of Calder-Sigma operators. Okay, so the focus of this, so that basically for Calder-Sigma operators, this top question here is answered. What is the optimal dependence on the AP characteristic so that this strong type inequality holds? We're going to shift our, I mean, this had plenty of motivation and applications, and I think historically is motivated by the study of quasi-conformal maps and regularity of solutions in the Beltrami equation. So PDE and geometric measure theory was definitely intimately connected with this. But we're observing that this inequality here has been well studied and understood. Let's shift our focus to the second inequality, where we replace the left-hand side with the weak type bound. We note the left-hand side here is smaller, so we can expect maybe better asymptotic dependence in the constant C, depending on this AP characteristic. And that's exactly what the main observation is here, and the main focus on this research that I'm presenting in this talk will be. So quantitative improvements can be made to the inherited weak type bounds. The strong type bound from the previous slide implies weak type bounds with at least the same dependence, but you can actually do better. And the theorem that culminates in all of this for the weak type bounds that we can cite is that the weak type bound from LPW to LP infinity W, when P is bigger than 1, excuse me, is the AP characteristic just the first power. In the previous slide, we saw that it was the AP characteristic of the first power and then the maximum of that with P prime over P. So for P smaller than 2, that thing blows up as P goes to 1, that exponent. Here it just remains constant at the exponent of P equals 1 the whole way. And we also have an admissible bound when P equals 1, where we get the A1 characteristic, but we pick up a log of the A1 as well, some additional logarithmic factor. And both of these are actually sharp. These were proved in a series of a handful of papers. First, by Lerner, Ambrosi, and Perez in 2009, they proved the weak type bounds for any p greater than or equal to 1 of AP times log of AP, which of course for the p greater than 1 case does not quite exactly match what I have stated here. Later on, the logarithmic dependence was removed, but it does match in the p equals 1 case the sharp upper bound that we have. Later on, this paper of seven authors, Hooten and Lacey, Martikainen, Orpinen, Reguera, Solero, Uriarte, Tuero, in 2012 showed that in the case where p is strictly bigger than 1, you can remove that logarithmic factor. You just have an AP condition here. I'll describe a more modernized, streamlined version of their proof. Here, I mean, I'm not going to have too much time, but I'll describe it very briefly at least the outline of it. So you can remove that logarithmic factor when p is bigger than 1. So that handles the sharp bound for p bigger than 1. And then there is a conjecture called the Muckenhout-Wheaton conjecture, which would have implied that this logarithmic factor in the p equals 1 case is not necessary. People were trying to remove this before, but actually quite recently, Lerner, Nasaroff, and Ambrosi in a really interesting analysis in PD paper showed that it's actually sharp. That you can't do better than this A1 times log of A1 in the realm of A1 weights for the endpoint weak type bound. Okay, so these are the sharp bounds in the previous slide for the strong type bounds, and these are the sharp quantitative bounds for the weak type bounds. And this is one of our main motivating theorems. We're going to first note two improvements of this, though, that this bound can be refined when introducing the Fuji-Wilson A infinity constant, which was introduced in the first talk this morning. And also it can be generalized to not only just Calder-Siegmund operators, but any operator satisfying sparse form domination. So a bigger class of operators. So again, not going to spend too much time on this because this was introduced earlier, but there's a characteristic A infinity, which is defined in this way, where M is the maximal operator, that is quantitatively smaller than the AP characteristic. It actually characterizes the membership of the weight being an A infinity, which is the union of all of these APs. APs are increasing classes of weights, so this is a very weak assumption, a very small kind of quantity to have, a weak assumption to impose on the weight. And you can actually refine the estimates from the previous slide. So the EP characteristic to the first power can be decomposed into an AP to the 1 over P times A infinity to the 1 over P prime. And since 1 over P plus 1 over P prime sum together to give 1 by Holder conjugacy, this refines the previous estimate. And also in the second one, when P equals 1, you can take this logarithmic factor and replace the A1 characteristic with an A infinity. So these refinements were actually proved in the original paper of these seven authors for P greater than 1. The Lerner-Ambrosi-Perez paper, where you had an A1 characteristic here in the P equals 1 case, had to be improved later by another analysis PD paper, Hooten and Perez in 2013. So they addressed this P equals 1 case and introduced this A infinity characteristic there. And also the bounds that I had in these previous slides generalized not just for Calderon-Siegmund operators, but for any operator satisfying sparse form domination, which again, in Manasa Vempati's talk, she talked about this, and also Nathan Wagner's as well, and tangentially in some other talks. But here's the definition. We say that an operator T satisfies sparse form domination if the bilinear pairing of TF with a G, which we can use to estimate the norms in any like weighted LP space, is controlled above by the average of F times the average of G times the measure of Q. So a very simple summands on the right. And we're summing over a very special collection of cubes. Cubes are in what we call a sparse collection S. And sparse is basically quantifying that these cubes are not quite disjoint, but almost disjoint in the sense that I wrote down here below. So the cubes, maybe they're not disjoint, but for any cube Q, in that collection, there exists a distinguished subset whose measure is comparable to Q, where those distinguished subsets are in fact disjoint. Calderon-Siegmund operators actually satisfy something more stronger, but we're just going to restrict ourselves to the sparse form domination because that includes more examples and we can treat that case. And for any operator in this class that satisfies the sparse form domination, which of course includes Calderon-Siegmund operators based off of work stemming from learners and many other authors at the time in this so-called sparse revolution, showed that Calderon-Siegmund operators satisfy this. We get these weak type bounds, these sharp quantitative weak type bounds for that entire class. Okay, now I can get to the main results, which I understand that I have only 5 minutes left in my talk. So I'm not going to, of course, explain the remaining like 15 or so slides that I have in full detail. But the main thing here is the theorem that motivates this entire work is that if you have an operator in this general class that can be treated by sparse form domination in some sense, and you have a corresponding weight in the corresponding AP class, Then you can get sharp quantitative bounds from LPW to the weak type LPW space that look like this. This is the best you can possibly ask for, and that's what you can do. So for the remainder of this talk, I would like to, if I had unlimited time, I would like to do this in more detail, but I don't have an unlimited time, so I'm going to do it with sparingly detail. The first goal will be to prove this theorem, give proofs of how this is actually going on. And in a recent investigation, we sort of rediscovered a new proof of the P equals 1 case, which in our opinion, which I'm going to describe a little bit more, has advantages. We give an original proof in the P equals 1 case of this that avoids two main difficulties. One, the reverse Holder inequality. All of the previous proofs of the P equals 1 sharp bound rely on the sharp reverse Holder inequality of A infinity weights to some degree. We don't use that in our proof, and they explicitly use the Calderon-Zygmunt decomposition, um, which is, if you're familiar with this setting, is not surprising, but our proof actually doesn't directly use that decomposition as well. So we rely more on elementary dyadic methods, and I'd like to say something about that given time. And then I would also like to describe other applications of the methods that we have, these new refined methods for the proof in the p greater than 1 case and our more original proof in the p equals 1 case. And one thing that I have slides prepared for, but I highly doubt that I'll have time to describe, is an application in the multilinear setting for multilinear Calderon-Zygmunt operators. Instead of just taking one function in and returning one function out, you take a tuple of m functions in and return one function out. Uh, but the general philosophy here was looking at quantitative weighted bounds. And instead of considering just the strong type bound, we look at the weak type bounds. The observation is that when you look at the weak type bounds, you can often expect and prove that you have better quantitative dependence on the weight characteristics. And that's what we're after. What we're trying to find are these quantitative bounds and proving that they're sharp. We've done this also in a few other settings. For example, in this limited range setting of RS limited range sparse operators of what we call LQ type, which includes certain types of square functions, that's in a paper of Zoe Neerath and myself, which was actually just accepted this morning into potential analysis. So I can say that I got the email like literally 1 a.m. this morning. So that was just accepted. The Bergman projection, where we, instead of talking about AP weights, we discuss BP weights. That's in a collaboration with Jiaola Chen, Nathan Wagner, who spoke this morning, and Zoe Neerath. And also, we're investigating this type of problem in the setting of commutators of Calderon-Zygmunt operators and fractional integral operators. That's in a joint work with Adam Mayer and my PhD student, Oscar Ramirez. But those are topics for another time because looking at my clock, I have 1 minute left. So let me just talk about the proof of how these weak type bounds go in the linear setting. Just very, very quickly, by sparse domination, we only have to consider the bounds for a sparse operator that looks like this. And for p greater than 1, the idea is to use what's called a testing theorem. So we refer to a theorem of Lacey, Sawyer, and Uriarte-Tuero from 2009, where they show that the weighted weak type LP norm is comparable to this quantity on the right, which is essentially it's a dual, like a localized dual testing condition. And then we want to verify that this condition here on the right satisfies the bound we want. And we can do that using a lemma of Cascante, Ortega, and Verbitsky, which was actually the same paper I believe was discussed earlier in the talk about Reese capacities, where you can give an equivalent norm on this dyadic operator. And then we have some other sort of AP weight type of things. This lemma here, I think, was known more classically. It's explicitly stated in a paper of Houdinin in 2014. So putting those together, okay, here's a bunch of holders inequalities and some analysis. There are inequalities that are involved, but you can prove this on one slide. I'm not going to go through the details, but they're here. You can take a screenshot if you're very fast. And in the p greater than 2 case, again, I can fit all of the computations on one slide to verify those. For the p equal 1 case, just for our time, I want to say that on presenting our new proof that is in our recently accepted paper of me and Zoe Neerath, where we prove that this inequality holds for sparse form domination operators. And I want to emphasize that our argument avoids the Calder-Sigma decomposition and the sharp reverse Holder inequality for A infinity weights. So the idea is to represent this weak L1 norm in terms of this type of bilinear pairing, which looks complicated, but the idea here is that this L2 pairing on the right no longer involves the distribution function or any powers of integrals. This is just like an integral of a product. And then we can apply the sparse form domination to where I'm circling right now in the middle of the page. We want to bound above this sum over averages of the function and the weights over a sparse collection and get the bound that we want. We can do this by reorganizing our sum using Fubini's theorem and organizing based on how much of the E prime measure, uh, how much of the W measure E prime takes up. Okay, this is technical stuff, so I'm going to go through quickly, but basically it's Holder's inequality and standard sparse tricks that don't involve anything fancy. It's just elementary dyadic stuff that first year graduate students can understand if you give them enough time, more than 1 minute that I'm giving you. Um, and then here we're using what's on the previous slide that you can bound above an integral of f on q by an integral of f on its distinguished pairwise disjoint subsets EQ. As long as the average of f is basically comparable to some quantity, you can do this. And then we do a couple more Holder's inequalities and get the bound that we want. But I don't want to go through that too much. We introduce a positive parameter and we choose it to be the correct constant to get what we want at the end. For multilinear operators, I have some slides prepared to describe what we can do, but the idea was for multilinear operators, sharp strong type bounds were known. The weak type bounds were inherited from the sharp strong type bounds, but we observed that you can do better. You can get a better dependence when you instead look at the weak type bound. Um, Things here are developed. Warren Ambrosi, Perez, Torres, Trujillo, and Gonzalez extended the weighted theory here. Sparse domination was extended by multiple authors basically at the same time with quantitative bounds. And in a paper of Zoe Neereth, myself, and Brandon Sweeting, we proved some inequalities that, again, are technical. But the important thing is that in these green regions here, those are delineating some certain collections of P1 and P2, like parameters P, where we observe that we have improvement over the strong type bounds um, from the inherited weak type, in the weak type bounds over the inherited strong type bounds. I'll stop here. Thank you very much.
Thank you. Is there any questions for the speaker?
I have a question.
Yeah.
Uh, so you mentioned the paper Buckley. He actually proved that A2 conjecture.
No, so no, he didn't prove the A2 conjecture. So, but I want to give him some credit there because he proved the lower bound. He proved the optimality of the A2 conjecture, and
Oh, okay.
people have been copying his work since then without, in my opinion, due credit. So he proved that this constant here is the best you can do for the Hilbert
Okay.
transform. This you can't expect to get any better thing here. But he proved an upper bound. I think that the exponent that he got was the AP characteristic to the P plus P prime, which is
Uh-huh.
of course bigger than this. So then that left open the open question of like, can we make the upper bound smaller and actually match the optimal lower bound that he proved in this paper?
Oh,
So
I see. So at
The A2
least,
conjecture was really I would call it Buckley's A2 conjecture. Like I think he basically is the one that conjectured it originally.
right. So he started this, I see.
Yeah, yeah. So it's been an open question for 20 years by the time that it was solved.
Okay. And
Any?
also for your with type bound with a lock, you said that you can completely avoid the Caron-Zipf decomposition.
Yes, I would claim so, yes.
Okay.
So there's been objections to this, which I have refuted in the past. So I've made this claim that you can completely avoid the Calder-Sigma
I mean,
decomposition
like
because
if you just want to prove basic with type 1 for Lebesgue measure, your proof can be used to avoid completely uh, the Caron-Zipf decomposition.
so in this statement here, we're assuming that imagine that you're trying to apply this to a Calder-Sigma operator. So then
Mm-hmm.
there's two steps. One is to prove that the Calder-Sigmund operator satisfies sparse domination,
Mm-hmm.
and then prove the bound for the sparse operator
Yes.
itself.
So in the first step, you use Caron-Zygmunt
In
decomposition.
the first step, you use the unweighted weak 1-1 bound of the Calder-Sigmund operator
Oh,
to
okay.
prove the
Okay.
sparse domination. In that step, you typically, and I'm going
Okay.
to make a caveat here to sell my PhD work, you typically use the Calder-Sigmund decomposition to prove the unweighted weak 1-1 bound.
Mm-hmm.
But I have a paper from 2020 in JMAA where I give a new proof of the Calder of the week one, the unweighted week 1-1 bound, the classical result of Calder and Zygmunt, which does not explicitly use the Calder and Zygmunt decomposition.
I
So there
see.
are technically ways to prove the unweighted week 1-1 bound. I mean, I don't want to be overselling my own work. It's pretty similar-ish to the Calder-Sigmund decomposition, but for example, maybe you don't need doubling property in the same sense that you do for the Calder-Sigmund decomposition. So there are some advantages and disadvantages. But there are ways to prove the weak 1-1 unweighted for singular integrals without Calder-Sigmund decomposition. Going through that route, then you can prove sparse domination without Calder-Sigmund decomposition, and then you can follow our argument to prove this without Calder-Sigmund decomposition. I'm stretching the truth slightly here to sell my own work, but you can follow that route, and those things exist. But um, that's a fair criticism and point.
Okay. Okay. Thank you.
Yeah, thanks.
Is there any more question? If not, let us thank the speaker again. So